It's a pleasure to be here to be speaking with you today. My name is Dennis Daly. I'm a Vice President of Connected Sensors at Omni Design Technologies. And today I will be describing our platform for connected sensor networks and the Internet of Things. So let me first introduce our company to you. What is Omni Design? We design, develop, and license disruptive semiconductor IP to enable the world's most advanced SoCs. Our company is headquartered in Milpitas, California, and also has a design center in Boston, Massachusetts, where I work out of. Now, Omni has invented the world's lowest power switched capacitor analog processing technology. And using this technology, as well as other proprietary technology that we have developed, we provide innovative solutions for ultra-low current analog mixed signal IP cores. Now, Omni has some of the semiconductor industry veterans, world-class technologists from MIT, and experienced entrepreneurs. Here you can see some of our leadership. Our leadership includes Dr. Kush Gulati, our president and CEO, sitting right here. He has a PhD from MIT and has many years of experience leading companies in the semiconductor industry, including semiconductor IP companies. Our chief technologist, Professor Harry Lee, is an MIT professor who's world-renowned designer in analog-to-digital converters. Our vice president, Sid Dutta, has over 2 decades of experience working at and leading engineering teams at some leading semiconductor companies. Personally, I received my PhD at MIT in low-power circuits and systems, and I've also worked for several years at Cambridge Analog Technologies and Maxim Integrated. Professor Pathan Halamulu from UIUC is our principal technologist, and Dr. Hyun Bu is our engineering director, and he received his PhD from MIT as well. So we have a very talented team. So now that I've given you a brief introduction into our company and our team, I'd like to describe our IoT IP platform. Now, but before that, I kind of want to describe what is the Internet of Things, because it means many things to many people. So how I define the Internet of Things as being physical objects embedded with electronics, software, network connectivity, sensors, actuators, security, and perhaps most importantly, energy. Because in many of these systems, energy is the most constrained part of it, and you need energy to actually do anything useful. So energy is something that's very important and must be considered, and we've designed our IP platform to really minimize the energy consumption. So there are many applications for Internet of Things, including smart vehicles, smart homes, smart factories, wearable electronics, and implantable electronics. And each of these applications has slightly different requirements. For instance, for smart vehicles, they require very advanced sensors, such as LiDAR, and they also require very high bandwidth communication, both within the car, from car to car, and from the car to the internet. When you look at smart factories, on the other hand, they need very advanced sensors and actuators as they interface with the physical world. When you look at the wearable and implantable electronics, these systems, on the other hand, have very stringent are and power constraints. So all these applications have slightly different requirements, but when you step back and take a look at them and think about the chips that are required to realize these systems, they actually share a common block diagram shown on this slide. And this block diagram is really driven at a high level by the physical objects that they must interface with. So first of all, you have to power this chip. So you will have DC to DC converters, chargers, LDOs that interface to the battery sources or the energy harvesting sources that drive these chips. These chips also need to communicate with other chips wirelessly or through a wired link. So you'll frequently have a Bluetooth LE or a Wi-Fi radio for them to do wireless communication. These chips must also interface with sensors and actuators. So you'll have accelerometers, gyroscopes, and you'll have these low-power AFEs and ADCs to interface to the sensors, and you will have low-power DACs and drivers to interface to the actuators and the speakers and the motors. Now, there's also core components in these chips. For instance, you're going to have a digital microcontroller, digital accelerators, and on the analog side, you're going to have some band gaps, some wake-up circuits, real-time clocks, retention memory, low-power LDOs. So a lot of core foundation IP. So what we have done here at Omni Design is we're assembling a platform of IP blocks so that you can come to us and we can provide you IP either directly from us or through our growing ecosystem of partner IP so that you can rapidly realize these complex systems with very fast turnaround time, low risk, and a very simple process. So some of the IP that we offer is shown in blue, and then in this grayish color, you can see some of our partner IP, and this is growing over time. And today I'm going to be talking about some of the IP that we're offering here in blue. Now, some common features of all of the IoT IP that we offer is that it's available in several process nodes. Today we support 28 nanometer through 180 nanometer, and we intend to support more nodes in the future. It's available in several foundries as well as flavors, and all of our IP offers very low current consumption and compact area so that these parts that you build are highly differentiated. We also make it operational down to very low supply voltages and robust to variations in the supply voltage, because many times these systems are powered by not a great battery or an energy harvesting source, and the supply voltage can move around. So you need to be really resilient to these supply voltage variations. Finally, we are making sure our IP licensing process, as well as the integration of this IP in your systems, is very simple and straightforward, so you can rapidly build these systems and make it very painless. So I'm now going to go through some of our building block IPs. So we have a bandgap family, and the bandgap is actually very important in these IoT systems because it's something that needs to be on nearly all the time, supplying voltages and currents to the system. And what we want to offer is a bandgap that's so low power that it consumes less power than the self-discharge rate of the battery, so you barely even know it's there. And this enables 10 years of battery lifetime, or it can enable energy harvesting systems, which can't be possible if you don't have a low power enough bandgap. So we have this nanoamp level bandgap. But at the same time, we want to give you the high performance that you can sometimes get with a higher power bandgap. So we've spent a lot of time to make sure the bandgap not only gets the low power, but also the high performance in terms of PSRR, a good temperature coefficient, a wide operating range, being very resilient to different supply voltages. So this is our bandgap family. Now, one implementation that we have built of this bandgap, shown here in 40 nanometers, it consumes 100 nanoamps of core supply current, achieves over 60 dB of both DC as well as AC wide frequency range PSRR, has a good temperature coefficient over a very wide temperature range, works down to 1.5 volts. And you can see the block diagram here on the right. We offer multiple current outputs, PTAD, CTAD currents for whatever the end user requires. There's also this output buffer that allows for a lower output impedance, which actually is quite important when you get to these nanoamp levels, because you can have very high output impedances if you don't do this. And the turn-on time can be quite large, which when you start thinking about production test can actually become a significant concern. And even in your end system, when you're running in normal mode, you don't want this to have too high an output impedance, depending on what it's driving. So this is an example of our IoT bandgap. Many of these IoT systems also require a clock to be always on. And you want this clock to be on all the time so it can periodically wake up the chip. Maybe you sense something or you send a wireless packet. But you need this clock to also be very, very low power. So we offer an RC oscillator and a crystal oscillator depending on your specific needs. Our RC oscillator consumes 200 nanoamps when it generates a 32 kilohertz clock. And it supports output frequencies up to 32 megahertz. It achieves 2% accuracy after a single trim. Our crystal oscillator can be used when you have a crystal resonator on your board, and it consumes 100 nanoamps of current. We also offer real-time clock logic that can be used to determine the time of day, the time of the year, and to generate interrupts when you deem them necessary. Now, ADCs are a key component of an IoT system to sense voltages from the battery, internal voltages, housekeeping signals. You also sometimes want to sense a current. So we offer a very flexible ADC family that allows for 8 bits, 10 bits, or 12 bits of resolution depending on your requirement. These are very low power consumption that scales with sample rates. So whether you need to do a sample once a second or millions of times a second, the power scales appropriately. And they're very flexible, so we want to be able to sample variable input common modes and signal swings, both single-ended and differential signals. And we also offer a 16:1 input mux, so you can sense a variety of signals throughout the chip with this one ADC. And it requires no special process options. Now, it's also important to note that our company also offers 14-bit gigasample per second, very high performance ADCs. These are a bit different than the ADCs I'm describing today, but if you'd like to learn more, please come by our booth 2018, and we can tell you more about these separately. Finally, one IP that we designed that I'd like to highlight are our sensor interface products, such as a temperature sensor. And this temperature sensor IP includes a core temperature sensor as well as a high-resolution ADC for a digital output. And it achieves 2 degrees accuracy after a single trim and sub-microamp current consumption at low digitization rates. And we also offer digital to analog converters that can be used to drive internal signals or off-chip actuators. So that's a brief introduction to some of our IP. I'll be able to tell you more after the talk if you'd like to learn more about our IP. But before I conclude, I'd like to talk to you and go through an example IoT system, a wearable. And you know, these wearables are pretty hot these days. There's the watches, the fitness monitors. I'm going to talk to you about a wearable, but a wearable for a moth. So this system is something I did nearly a decade ago when I was at MIT doing my PhD. This was before IoT became a buzzword, and the buzzword at the time was actually called wireless sensor networks. But the system was very similar. So I worked with several colleagues, and we wanted to build a system to wirelessly control the flight direction of this moth. So it actually had extreme IoT requirements. We needed it to weigh less than 1 gram, which is actually less than half the weight of a US penny. It was powered by a small coin cell battery, which couldn't supply very much current, peak current, or average current. We needed a low power wireless link. We had a microcontroller, flash memory, DC-DC converter, crystal oscillator, a stimulator that interfaces to the central nervous system of this moth. So when you look at this block diagram, it actually fits very nicely to that IoT block diagram I showed earlier. So we really were building an IoT system nearly 10 years ago. So we worked many long nights building together an ASIC and combining with a few off-the-shelf parts, and we were able to build the system, mount it onto the moth, and get the moth flying in a wind tunnel. And here you can see an example of the moth flying with our wireless chip on there. It's flying to the lower right. We would then send a wireless command to this moth. It would stimulate its nervous system, and in response, it changed direction to the left. So we were able to show this a few times in this wind tunnel, and it was pretty interesting to see this. These results were pretty well received, published at the ISSCC conference, winning the Best Student Paper Award that year. And it was a heck of a lot of fun to work on this and really see a multidisciplinary stuff from the system level down to the very circuit level. Now, one limitation I discovered while building this was that the power numbers were too high for many of the components available. 10 years ago, there just weren't these SoCs available. So what we want to do here at Omni is provide our customers the IP such that they can build such a system that can last for months, if not years. Maybe the system might not be for a moth. Hopefully it's for humans and we can do some other stuff with it. But really that's our goal, to enable such a system, but with a 10-year battery lifetime. The other thing I learned over the course of my many years working on such systems is that to build a differentiated system, you need to differentiate on many levels simultaneously. The architectural, circuit, hardware, system, software, and maybe even business model. You need to be good in all of these and excellent in hopefully a few of them to really build a compelling part that's going to have success in the market. So what our goal here is at Omni Design is to build an IP platform that lets our customers build these differentiated systems and not need to worry as much about the circuit level, because we'll make sure that your parts are differentiated in that space. So that's really our goal, and I really appreciate you attending this talk. If you'd like to learn more about our IP, I'll be sticking around after, and I'd love to chat with all of you. Our booth is booth 2018, and we'll be here for the next 2 days. And also our president and CEO, Dr. Kush Galati, who's sitting right here, he will be giving a talk on this stage tomorrow at 5 o'clock. He'll be describing more introduction about our company, more of our team members, and also describe our high-performance ADCs. So I encourage you to attend that talk. And again, thank you very much for your attention today.